A photonic machine sitting in a laboratory in Hefei, operating on beams of light, rather than superconducting circuits chilled to near absolute zero, has posted sampling results that the research group behind it claims would take a classical supercomputer an implausible stretch of time to match. That claim has not yet been independently reproduced at full scale, and that distinction matters more than any headline number attached to it. At the center of that claim sit two irreconcilable architectural bets: a Western gate model consensus backed by some of the most heavily funded quantum programs in the world, wagering that universal and error-corrected logical qubits are the only road to genuine quantum advantage, and a Chinese photonic path built around a machine called Jiuzhang, wagering that specialized sampling on photons can deliver real-world value before full error correction ever arrives. What follows is a pricing of where those odds sit today, what evidence has moved them, and what results would move them next. The contested anchor running through every weighing here is specific: the first error-corrected logical qubit performing a task with demonstrated utility, not a sampling demonstration, not a physical qubit benchmark, not a vendor roadmap projection, but an error-corrected logical operation solving a problem that a classical machine cannot match at equivalent scale and cost. That threshold has not been crossed by either bet. It is the finish line the odds are pricing, and it remains open. Two bets, then, laid clearly before the weighing begins. The gate model consensus, backed by the programs at IBM Quantum, IonQ, and PsiQuantum, holds that the path to useful quantum advantage runs through universal and programmable machines that correct their own errors and scale their logical qubit count without proportional loss of fidelity. Superconducting versions of this machine require dilution refrigerators running at temperatures colder than deep space and specialized fabrication processes that have historically depended on a small number of Western-controlled supply nodes. Trapped ion versions post higher gate fidelities on individual operations but scale more slowly. PsiQuantum's variant bets on photonic fault tolerance built through silicon photonic foundry partnerships at a scale that does not yet exist for quantum hardware. The shared wager is that only a machine which can be reprogrammed, which corrects its own errors, and which generalizes across chemistry simulation and optimization and machine learning inference can deliver advantage that matters beyond a single demonstration. The Jiuzhang path, developed by the Pan Jianwei group at the University of Science and Technology of China, bets differently. Jiuzhang encodes quantum information in photons rather than superconducting circuits, runs Gaussian boson sampling tasks on an optical interferometer, and does not require cryogenic cooling at the same depth as superconducting machines. The constraint that shaped this bet is structural. Restrictions on access to superconducting fabrication ecosystems push the program toward a photonic architecture with a different cost curve and a different supply chain exposure. Single photon sources, optical interferometers, and photon number resolving detectors form the backbone of a supply chain China has been actively building domestically. The wager is that this specialized advantage is real, expandable, and arrives before the gate model consensus crosses the fault tolerance threshold. The first weighing turns on whether Jiuzhang's results constitute a genuine quantum speedup. The University of Science and Technology of China group has published results in peer-reviewed journals, which clears the preprint threshold, and the results describe sampling speeds that the group's own figures suggest classical machines cannot replicate at the same scale. The rebuttal from the skeptical read is clean. Boson sampling is not a useful computation. It produces samples from a probability distribution that is classically hard to simulate, but no commercial or scientific problem is solved by that output alone. The sampling task is impressive. The output is not, on its own, valuable. The evidence here clears the bar of peer-reviewed publication, but does not clear independent confirmation at full scale. Research groups working on classical simulation of boson sampling have raised methodological questions about the scaling assumptions underlying the hardness claims, and that debate has not resolved. The odds move modestly toward Jiuzhang on the authenticity of the quantum speedup, and modestly toward the skeptical read on whether that speedup constitutes useful advantage. The net position, lying roughly flat on utility, slightly favorable to Jiuzhang, on the basic question of whether the quantum phenomenon is real. The second weighing examines the gate model consensus on its own terms, and this is where the Jiuzhang path loses a metric cleanly, and the loss is not recovered in the same breath. IBM's roadmaps have delivered physical qubit counts scaling across successive generations, and those numbers are real and verifiable. But physical qubit count is the least informative figure in this race. encoding a single reliable logical qubit from physical qubits with current error rates requires, by rough estimates circulating in the research literature, somewhere in the range of hundreds to thousands of physical qubits per logical qubit, depending on the error correction code and the target fidelity. A machine advertising hundreds of physical qubits may be operating with a handful of reliable logical ones, if that. IBM's roadmap projections on logical qubit timelines are vendor claims, not peer-reviewed results. Now, the clean loss for the photonic path. On the metric of gate speed and programmable circuit execution, Jiuzhang trails and the gap does not close by adding more photons to the sampling network. A superconducting transmon can execute gate sequences at nanosecond timescales across a programmable and reprogrammable circuit. A boson sampling machine is not reprogrammable in the same sense and cannot run arbitrary quantum algorithms. On programmable gate speed for general computation, the photonic sampling path plainly comes second, and the odds priced at loss at face value without qualification. That concession made, the skeptical read on the gate model side is symmetric. The distance between current physical qubit machines and a working fault-tolerant logical qubit system is not a linear engineering problem, and no independent benchmark has yet confirmed logical qubit advantage on a task with clear utility. A message transmitted across a noisy channel requires not one copy but many, with enough redundancy that errors can be identified and corrected from the pattern of the whole. A logical qubit works on the same principle. It is not a single physical qubit, but a structured collective whose joint state encodes the information reliably, even when individual members are disturbed by noise. The overhead is the price of reliability, and on current hardware, that price is steep enough to explain the gap between the physical qubit numbers on vendor slides and the logical qubit counts that would actually run a useful algorithm. The odds on near-term gate model utility move toward the skeptical read. The consensus bet is real and well-funded. The distance between where it is and where it needs to be remains the largest unpriced gap on the board. The third weighing brings PsiQuantum into the frame. PsiQuantum's fault-tolerant photonic approach represents a Western convergence on photonic methods, and one reading of that convergence is that it validates the architectural direction China pursued with Jiuzhang. The rebuttal to that reading is precise. PsiQuantum is building a fault-tolerant universal quantum computer using photonic qubits and error correction, which is a fundamentally different machine from a boson sampler. The fact that a Western firm is building photonic hardware validates photons as a physical substrate. It does not validate boson sampling as a path to general advantage. PsiQuantum has announced silicon photonic foundry partnerships and attracted substantial private capital, but has not published a working prototype result at scale. This is a well-funded bet, not a demonstrated result. The odds move slightly toward the photonic direction broadly, while the two photonic approaches, Jiuzhang's sampling architecture and PsiQuantum's fault-tolerant universal architecture, are competing against each other as much as they compete against superconducting machines. The line on photonics broadly sharpens. The line on Jiuzhang's specific approach that does not move as much. The decisive weighing is the one that most directly prices the constraint became Catalyst's thesis. The restriction on superconducting fabrication access pushed the Jiuzhang program toward a photonic architecture that sidesteps cryogenic and fabrication bottlenecks entirely. Jiuzhang does not need a dilution refrigerator running at millikelvin temperatures. A quantum state's coherence time, the window during which it remains quantum before noise collapses it into a classical outcome, is measured in microseconds on many superconducting systems, roughly the time it takes sound to travel the length of a fingernail, and every gate operation and every correction step must complete inside that window. The photonic path carries different coherence constraints and different manufacturing dependencies. The bet that appeared to be a consolation prize turns out to have a different cost curve and a different exposure to the supply chain pressures that shape the race. The strongest rebuttal is structural. If the gate model consensus builds fault-tolerant logical qubits first, the sampling advantage becomes irrelevant. A universal and error-corrected machine can, in principle, simulate a boson sampler and solve the problems a boson sampler addresses, plus every other problem the application landscape demands. Jiuzhang wins only if it can demonstrate utility before gate model machines reach fault tolerance, and only if the useful applications of boson sampling turn out to be real rather than theoretical. The application case for Gaussian boson sampling in molecular simulation and logistics and financial modeling is active research, but peer-reviewed utility demonstrations at production scale remain sparse. 3 reasons the favored position could still lose, synthesized. The classical hardness assumption underlying the boson sampling advantage is actively contested, and the preprint literature on classical simulation methods has moved faster than most observers anticipated. The gate model path faces an equally structural problem. Error rates have not consistently cleared the fault tolerance threshold at scale, and quantum computing roadmaps have a documented history of sliding. And critically, neither bet has produced a result that a classical computer cannot replicate on a problem with clear commercial or scientific value. The anchor remains unclaimed on both sides. Synthesis. Both bets are alive, neither has closed, and the evidence that would decisively move the line has not yet arrived. Pricing the odds now means pricing which bet gets there first. That forward pricing is where the real uncertainty lives, and it deserves real substance rather than a recap of what came before. The first catalyst to watch is an independent classical simulation of Jiuzhang's sampling regime. If a research group outside the University of Science and Technology of China publishes a classical algorithm that efficiently samples from the same distribution Jiuzhang demonstrates, the quantum advantage claim collapses without any new quantum hardware being built. This is the single result that most directly prices the skeptical bet on boson sampling. If it lands, the Jiuzhang line falls sharply, the specialized path thesis loses its anchor, and the supply chain independent story remains true, but the result that validated the bet evaporates. The gate model consensus becomes the only credible road to general advantage, and the odds shift decisively in that direction. The second catalyst is a peer-reviewed, independently confirmed demonstration of a fault-tolerant logical qubit from the gate model side, executing a circuit on a problem with commercial relevance. Not a physical qubit benchmark, not a simulated error correction result, but a genuine logical qubit performing useful work that an independent team confirms. This catalyst would not merely move the line, it would begin to close it. The Jiuzhang path retains value in its specific sampling niche, but the long-term general advantage race would effectively be called. The analyst prices this as the most consequential single event on the forward calendar, and also the one with the most uncertain timeline, given the gap between current physical qubit machines and the fault tolerance threshold. A third catalyst works in the opposite direction. If the University of Science and Technology of China, or a collaborating institution, publishes a peer-reviewed result connecting Gaussian boson sampling output to a specific molecular simulation or optimization problem, with output that a classical machine cannot match at equivalent speed and cost, the utility gap in the Jiuzhang bet closes without requiring the machine to become universal. That result would validate the specialized advantage wager on its own terms and force a repricing of the gate model timeline pressure, because if specialized photonic machines are delivering utility before fault tolerance arrives, the urgency calculus of the consensus path changes. This catalyst moves the Jiuzhang line meaningfully and is the result the photonic sampling bet most needs. A fourth catalyst sits in the Western photonic lane. If PsiQuantum announces and independently confirms a working photonic chip produced at a silicon photonics partner at a scale consistent with its fault tolerance architecture, the photonic manufacturing thesis gets its first real evidence. That result would move the line toward photonic fault tolerance and away from boson sampling as the photonic approach with credibility, applying indirect pressure to Jiuzhang by demonstrating that the West has its own photonic path aimed at universal computation. The net effect on the Jiuzhang versus gate model matchup would favor the consensus side while validating the photonic substrate both programs share. The evidence priced honestly favors the gate model consensus on long-term general advantage, but by a margin that is narrower than the Western consensus assumes, and that Jiuzhang's results have meaningfully compressed. The photonic sampling path holds a real, near-term position on specific problem classes, and the supply chain independence that restrictions produced is a durable structural fact regardless of how the sampling advantage debate resolves. The constraint that redirected a superconducting program toward photons did not produce a lesser machine. It produced a different bet with different cost curves and different vulnerabilities, and those differences are now precisely what the field is pricing. The analysts read, gate model consensus as the more probable long-term winner, Jiuzhang is a live line on near-term specialized utility, and the single largest uncertainty on the board is not which architecture is theoretically superior, but which one first demonstrates that its theory touches a real problem a classical machine cannot solve. The anchor, a corrected logical qubit doing useful work, remains uncrossed, which means neither side has closed the book and the odds are still moving. Until that threshold is crossed, the race is not a matter of waiting for the inevitable. It is two bets whose odds are close enough that the next result, wherever it comes from, and whichever architecture produces it will price the line in a direction the current evidence cannot yet determine. Which bet would you back with your own capital? The gate model consensus racing toward fault tolerance, or the photonic sampling path wagering that useful advantage arrives before full error correction? The line is open in the comments. If you want the next result priced when it lands, subscribe. This channel covers the odds as they move, not after they close.